And then the sizing, we did already talk about that, 250/66, that table, how to size that. And so you know how to use the table now to. Now let's look at the termination of the grounding electrode, which is in 250.66. If you read in there, we'll start looking at the 68A. We'll talk about accessibility and what it says. Any ground connection that's being used for your, for your grounding electrode conductor to grounding electrode, you must have accessible, which means that we will typically put a plate that will get a cover once the sheet, in this case the sheetrock looks like it's going to go over this, and so once the sheetrock goes over this, we would have the hole available where we could actually just put a normal 2-gang plate to cover it up, and then we could always do a visual inspection of it and that connection years later. So that has to be accessible and be able to visibly access it, so you can check the connections and make sure you always have a good connection in here. Kind of sloppy on the work. I kind of noticed the ground wires just, I don't know why they did it the way they did it, but it's kind of, normally we want to go in straight lines and not make loops, and whatever reason happened here is they were very sloppy with their work. But normally I would have came across here and went into this hole more direct instead of having loops, because especially with lightning strikes, if this does get affected by lightning, you may have a large discharge that, as it makes it around these corners, you may literally jump out of the wire. Because of the forces being applied to those electrons from behind, you're talking about possibly from 1 million to 10 million volts of pressure being applied to those electrons to flow to Earth, and it would use this path here to get there. Also, there is an exception there, even though we spoke about accessibility. In the case of an encased or buried grounding electrode conductor connection isn't required to be accessible, but the ground clamp has to be listed for direct burial according to 250.70. And so, a lot of times people struggle with these ground rod connections, whether they need to be accessible or not. And it used to be years ago they would have to be. The code has actually clarified this and saying no, as long as you have the proper connection. These can be mechanical connections, or it can be what we call exothermic welding connections, where we actually use we use a high heat source that will actually melt the wire onto the ground rod. So it's CAD welding is also known as CAD welding. Technically, it's called that's a name brand, but it's called exothermic welding. So where we actually make the connection so it's permanent, welded on, basically. So let's look at the integrity of the metal water pipes. If we are using the metal water pipe, we have to actually bond around it. So in this case, because the continuity would not be achieved due to the water meter, and most water meters actually have plastic fittings anyway. And even there's also something called a backflow preventer that usually will be outside of the building. And the backflow preventer allows, so if you have a well on the property, typically you might have to use a backflow preventer to, stop any flowing of the water back into the city water, because possibly you might contaminate, especially if you have a well, they don't know the quality of the well. So backflow preventers also have plastic fittings, and usually have to bond around these fittings. So in this case, we bonded, whether it was a water meter or a filter or a backflow preventer, because they're all usually plastic fittings. We would have to actually run a wire around the device to ensure continuity of the device, and that's what we're talking about here in 250.68b, is maintaining the integrity of the water pipe. Let's look at 250.70, which is the grounding electrode conductor termination fitting. Something that we don't, that I want to make you aware of. I think it's an important point, is that all these fittings have a material that that has been approved to be used. So for example, aluminum, copper, and so on. And that's true of wire nuts, of tons of things. Any termination, they will usually have the ALCU, AL being aluminum, right? So we will typically see it'll say AL, or might have a slash like CU for copper. And so these fittings have to be listed for the material. If you're using copper on there, it's got to actually have the CU, and the size of wire will be stamped on the side of this that's allowed to be used. So this is actually in what we call an acorn termination fitting or connector, acorn, because it's shaped like an acorn. And so you press the rod against the wire. Make sure you put the wire on the back side and not where the threaded bolt would actually go into. That usually is for the actual ground rod. And here is one that's actually approved for direct burial, as I mentioned before. In the case of where you have a wire that's terminated underground, we have to make sure that it's stamped direct burial on there. And then also the other thing is that you're only allowed to have one conductor on these single terminations, which in this case you can kind of see that we have two wires that are terminated on there, and that's not allowed. What would have been the proper way would have been to allow this wire to be continuous from one pipe to the other. So I would have ran the wire from the service down, go through the acorn fitting that's direct burial rated, and also run it over to the other ground rod, all in one piece. So we would have not cut it. At this point, I would have to put two acorn fittings here, one for each wire, the wire coming from the panel, and the wire going out to the other grounding electrode would actually have to have a separate termination fitting. Let's look at 250.80. And one of the things there it does say is that, well, first of all, it says metal component installed in a run of underground non-metallic raceway having a minimum cover of 18 inches aren't required to be bonded to the service neutral, supply side bonding jumper, or grounding electrode. What it's saying is that if we did run PVC from this box, but we choose to run a metal pipe in here, and this would be the metal pipe. This would be typically rigid, okay, which would be RMC. And the reason we would do that is if you've ever pulled through PVC, well, the first time it happens, it'll be interesting. If you use elbows here, this 90 is an elbow. If you use PVC, the rope has a tendency, if you're pulling with a rope, it will cause friction against this pipe, heating the pipe up and then melting it, allowing for you to cut into the PVC. So what happens is we end up having to run rigid pipes for these 90s, especially for long pulls. There's nothing in there that says that we have to do this. What it says, we just know that if we ever had to do this work, it would be a major disaster. Especially if this was under the building and we're trying to pull the wires in, and this pipe were to, we would literally cut it with the rope it would have been an accident. Then it's very hard to solve that problem, which would mean that we would have to dig up this 90 with a backhoe probably and replace it. It would be a very costly endeavor to actually do that. And so in order to avoid that, hindsight's 2020, but to avoid this is we put a rigid elbow in here. And what it's saying is that if you have a metal component here that's below 18 inches, you don't have to worry about that. You don't have to do that. Um, 250.86 talks about enclosures and how we would actually achieve the equipment ground connection or bonding jumper at the boxes. So lock nuts typically will serve, but also bonding lock nuts, which actually are a little bit different than a lock nut. They actually have a little screw. Here we can see a lock nut with the actual screw that would actually allow you to get a really good connection for the equipment ground or bonding jumper in the box. So that you would see basically in this upper right hand corner here is we're looking at this corner here. We're saying bonding lock nuts. The other thing is we could do is, we could also achieve the equipment ground being attached to our equipment through this bonding jumper. And so that's another way to carry the equipment ground through the system. In 250.92b, it talks about the ring knot knockout entry. For example, these are called concentric knockouts. Concentric knockouts only have a small piece of attachment of metal. Everything else is kind of punched away. Let me see if I can zoom in. So here we can look at and see the concentric knockouts, which are different than eccentric knockouts. And eccentric means off-center, which sometimes when people are called like eccentric, they're saying somebody's off-center, off-normal. Concentric means that all the circles are centered on each other. And so here we have concentric knockouts. But the thing is, this area where you see the line is basically where it's punched out, and where there isn't a punch here is where you have the actual connection of the ground. Well, the problem with that is that if we were using the inner circle, you only have a small strip of actual path for the equipment ground, or the grounding pathway to actually to go through. So we are required to actually have bonding bushings in some of these. It's dependent on a few different requirements that we'll look at here in a second. And those situations would be at the service. We would be required to actually go ahead and put jumper wires to carry the equipment ground through the system, through the conduit, through the lock nuts, through the equipment enclosure, and we would put a bonding jumper to achieve that, and that would be at the service. It's also required for any time we have 250 volts to ground, so we're talking about 277 volt systems would also have the same requirement. Now if we did have eccentric knockouts, which eccentric knockouts would be a little bit different, that the circles would be, let's see if I can do, it's terrible. The eccentric knockouts would be off center. We'd have enough ground. So for example, in eccentric knockouts, because we're off center, the lock nut would have a little bit more meat to, or metal to actually make contact with, versus the concentric knockouts that were dependent only on the little tabs that are not punched out to achieve the pathway to conduct the ground pathway, for the equipment ground. And so eccentric knockouts would be required when we're dealing with the higher voltage. And so here would be an example of a box with eccentric knockouts. And so here we can see the center 1/2 inch, and you can see the 3/4 inch punch. So if you did do 1/2 inch, and this box would allow me to use it for 277 volts systems, 277 480 volt high voltage systems, and concentric is allowed for 120 volt 208 three-phase systems or single-phase systems. But when you get to the higher voltage, these are not, we'd have to do eccentric knockouts for the boxes itself. 250.92b3 also addresses the issue of the raceways being considerably suitable bonded by threadless fittings and made up tight. And so you would not, you could use these. Normally we use threaded type fittings, so we can avoid the issue of whether we are made up tight, and also whether it's suitably bonded at that point. So it always ends up being a question mark, whether threaded fittings versus screwed fittings, whether the screwed fittings would be adequate for that purpose. So normally I've avoided, we always use threaded fittings on these type of connections when it comes to at the service. 25096 addresses the issue of bonding of, for example, if we had other systems, like at the panel. So we're not talking about the service here. We're talking about maybe a panel somewhere. So in this case, we're using a reducing washer here, and this always becomes a question of whether we have an effective ground fault current path by using these type of bushings. So usually the reason why we use those reducing bushings is because somebody screwed up. They punched out the bigger hole, and you're running a smaller conduit into that bigger hole. So we use reducing washers to be able to achieve that. So in this case, I would actually have to put a bonding jumper, because it's very hard to get the listed washers that will allow me to carry and be listed for these type of applications, especially with the higher voltages. 277 40 80 volt systems will run into a problem. We cannot use the washers for this type of application. And 250.97 does address the issue on 277 40 volt systems, where, for example, we are talking about that reducing washer, and so what happens with the eccentric versus concentric and so on, and properly bonding that in order to achieve the proper connection for the equipment ground. Okay, so again, ring punched have to be eccentric type, and so on. 250.98 does address whenever we have expansions that are expansion joints, and those are bonding loosely jointed metal raceways. What that means is sometimes we have in larger buildings we'll have areas where there's a separation that allows for seismic activity. So there's kind of like two separate buildings, but they're attached together. They're just kind of, there's a big gap between them. And they do that specifically for earthquake-prone zones, and so we may have an expansion joint that is loose that basically moves back and forth, or what typically I've done, instead of using these fittings that actually move in and out, is we'll use flex, and we'll create a loop in this type of connection. With flex, we'll go pipe, flex, and then back to pipe. And the reason is because it allows for that flexibility during earthquake or seismic or any type of movement that may be occurring within the building, the two buildings. And so we have to put a bonding jumper across those metal raceways, and 250.98 addresses that. So 250.104A1 addresses about making sure you bond everything, and what they're talking about is, for example, metal water piping systems, sprinkler pipes must be bonded to any of the following, which here we can see that the water pipe could be bonded to the metal structure as long as we put a bonding jumper between the water pipe and the metal I-beams, or we can bring the wire into the service. So it's giving us different options, or we can go directly to the UFER ground, in this case at the bottom. But it's telling us that we need to make sure we take water piping systems and also sprinkler systems that must be bonded, and that's a requirement. So here we can see where we took the water pipe and we bonded it across over to the metal service, which is the metal structure of the building, which is also bonded to the service at some point. So if anything did become energized on the water pipe, then we have a path for it to go back over to the service and then get it back into the system through the main bonding jumper. And also in 250.104B1 talks about metal piping such as gas or air that are likely to become energized are permitted, and it does say permitted, and there's a reason why it says permitted, to be bonded to the equipment grounding conductor for the circuit that is likely to be energized. The piping is that in some jurisdictions they don't allow you to tie the gas piping to the electrical system because they're concerned that any energy that's imposed onto the gas piping may cause an explosion. And so, for example, San Francisco was like that. I did a job in San Francisco where they did not want us to bond the gas pipe, and that they were more concerned with the piping becoming energized and potentially blowing up. And this is closer to the downtown area of San Francisco. So, one pipe exploding in one building can cause multiple explosions through all the different buildings. So that's going to be up to the local jurisdiction on whether that's allowed or not. But definitely on the air pipes, air, like if you have compressed air system, then that could actually become. But again, it says are permitted to be bonded, are permitted, and so you can do it. It's not necessarily required unless the jurisdiction says otherwise. In 250.106, it addresses about lightning protection system. If you did have a lightning rods and you had a wire, basically, usually they go on the outside of the building actually, and if you do have a lightning protection system, that at some point it will have to be bonded to the grounding electrode system. So we make sure there's no potential difference between the two wires, and that we dissipate the energy into the earth at all points, potential, for that potential, and not creating a potential difference between 2 points. Now, part 4 is about the equipment grounding conductor, and this is actually where we spend a lot of time within our electrical systems, pulling a lot of these wires. So this is definitely an important section, but it's actually a very simple section. And so let's look at Article 250.112 or 112. It says that in there it says that specific equipment, exposed metal parts of equipment and enclosures must be connected to the circuit equipment grounding conductor. Okay, so it says that you're going to have to make sure you tie everything to the equipment grounding conductor, the EGC. It will need to be tied to everything. And also for grounding of circuits less than 50 volts, and that's 250.112 I, or I think that's part 1 actually, 1. So it says for low voltage systems that are less than 50 volts, basically, you don't have to be tied. So if you have any metal parts in those systems, they're not required to be tied in those areas. Cord and plug connected equipment will be, so 250.114 does require that the ground prong is available on these type of cords, so we can actually carry the ground to our equipment. There is an exception for that, and that would be if you have double insulated type equipment. There is no ground prong there in that type of situation where we have the internal components of the equipment that are insulated from the external metal components of the equipment, and that's called double insulated, and that would be the only exception where the ground prong would not have to be present on the cord. 250.118 addresses as in what is allowed as an equipment grounding conductor. Okay, so it says that we can use metal pipes as our equipment grounding conductor. So RMC, IMC, EMT, flexible metal conduit, liquid flexible metal conduit, and that's that actually has an inner. So it's not just liquid. It's not a plastic flexible pipe. It has a metal interior in there, and you're able to carry the ground through that LFMC down here on the bottom we're looking at. The only thing is if we're dealing with like type NM, or that would be flex, if we're dealing with MC cable, And if we're dealing with AC cable, then we have the issue of the conductive, whether we have to have a ground inside of there. There is a MC cable that's armor listed as EGC, or equipment grounding conductor, an AC cable that has a redundant ground in it, and so it's a little wire that wraps around the AC cable, and those cables would be allowed to be carried. You would be allowed to carry the ground through those. So I will tell you that RMC, IMC, EMT, FMC, LFMC, I've always pulled a ground wire. PVC obviously is non-conductive, so it cannot carry the equipment ground. So we actually literally are required to pull the ground in that. But I've always pulled a ground in all of these type of conduits, no matter what, because you are dependent on the connections. For example, if you have a set screw on the FMC or the EMT. Now, FMC and LFMC are limited in the distance that you can actually run before that can be used as a ground, like an equipment ground. Okay, so you're still, that distance is going to limit you. So there's no point of actually. You might as well just run the wire, is what it comes down to. It's pretty cheap to do that. It's a better installation, and again, if anything goes wrong, you have the wire as a backup, and you're not dependent on the EMT, like somebody forgetting to screw the connector on the EMT, which happens all the time on the job site. So we are required in 250.118 note to have an effective ground path, which means that whatever we choose, we have to make sure that it's a effective ground fault current pathway, which means that conduit technically is only good to about 200 feet. So if you were using the EMT, it's limited in distance. So every type of conduit has its own impedance under those conditions, depending on what the fault currents likely to be imposed on it. And so again, that would be a situation where where sometimes it's not worth it. 200 feet is easily achievable, and so on. We can look at an example here. You have a 100 amp device, so we have a breaker that's 100 amps. We have a short circuit. The number 3 wire, which is what we're using for 100 amps, has some resistance, but the 200 feet of the conduit in this case would have a certain amount of resistance, and we can figure out that the fault current likely to be imposed on this would be about 583 amps, so about 500%. And so we have to make sure that that pathway is a low impedance pathway to facilitate the operation of the breaker, and that's the whole purpose here of our equipment ground. We're trying to create an alternate pathway, controlled pathway back to the source through the bonding jumper back to the transformer, and allowing the breaker to trip because of that high amount of current. Well, if you have too much resistance in the system, this would not operate as it's supposed to. So that we have to be very conscientious of that part. That's why I've never sat there and tried to fight the issue of whether I should pull a ground wire or not in my conduit. We were talking about flex, whether we can use flex as actually a equipment grounding conductor, and yes, but there's some limitations according to 250.118 number 5, and so it says the raceway terminates in listed fittings, so we have the proper fittings for it. The circuit conductors are protected by a 20 amp overcurrent protected device or less, so it's saying a 20 amp circuit or less, or 15 amp. Not larger than trade size 1.25 inches, and the combined length of the FMC fault current path does not exceed 6 feet. So that's the longest we can actually use, that is for 6 feet, which is really limited. That's why it's not even worth it, because we may have 7 feet. At that point, you might as well just run a ground wire. Again, too many small little details for me to try to avoid to actually running a ground wire. So if you've been in one of my classes, you know how much pressure I put on you in regards to the green wire only being used for the purpose as an equipment ground. In this case, we can see where somebody ran out of blue wire. They had black wire, red wire, and they ran green wire for an ungrounded the ungrounded circuit, probably the C phase in this. It should have been blue, and down below you can see black, green, and red, and that's wrong. This is totally not acceptable. And as I've yelled at you many times in my classes, the two colors that are basically dedicated for a very specific purpose are the green wire, and it's only specifically can be used for an equipment grounding conductor, or the white wire can only be used as a grounded conductor, white or gray, right? So those are dedicated colors that cannot be used for anything but those specific purposes. We can get crazy with the black, red, blues, and purples, pinks, and whatever color you want to use out there. But those other colors are dedicated, and it's a violation of the code. But 250.119 does indicate, does talk about the identification of the equipment ground, how it can't be used. That color can only be used as an equipment ground. And this is my favorite part here, is the sizing of the equipment grounding conductor. And most, we're going to be using this quite a bit out in the field. 250.122 is one of those top 10 sections of the code that you need to have. So there's my top 100, and then there's my top 10. This is a top 10 code article that you will use in the field, and you will always be going back to this to double check things, okay? To double check what is the size of my ground wire, because it isn't the same as the regular circuit conductors, right? So it's not going to be the same size as your neutral, and it actually can be smaller because it's only being used during fault conditions, and it's not a current carrying conductor. So let's look at 122A, and it says the size of the equipment conductor, the wire type, is sized to the circuit's overcurrent device rating in accordance with table 250.122. So in this conduit, I have my circuits coming in, and I will run a equipment grounding conductor into this conduit. The wire coming into this conduit is sized based on the breaker that protects the wires that go into the same conduit. So for example, here we have a 40 amp breaker. We can run a number 10 wire, which is different than the branch circuit protection. And we'll look at that here in a second. I'll show you that. Or if we're looking at 125 feeder protection, then we run a number 6 wire with those wires that would be feeding the 125 amp circuit conductors. So let's look at 250.122, and it says minimum size of equipment grounding conductors for grounding raceways and equipment. And here it does say that it's important to always read these things carefully, because here it's saying not the size of the wire coming in, but it's actually saying the rating or setting of the automatic overcurrent protecting device in the circuit ahead of the equipment conduit or so. So if we had a 125 amp breaker, we're going to use the 200 amp rating, and we're going to run a number 6, and that's how we got the in that scenario we saw before. Let me see here. In that scenario where we had 125 amp feeder protection, we calculated the ground wire to be a number 6. What we did is we went to 250.122 and actually looked on here and saw that anything up to 100 amps was a number 8, but anything up to 200 amps minimum size was 6. So we're somewhere between over 100 but less than 200, and so that would be good for what we were required to have, the number 6. The other one was having a 40 amp branch circuit protection. What size of wire? Well, here it says number 10. Well, how do we find that? We actually went to the table. A number 10 wire is good up to 60 amps. So a number 10 is good up to 60 amps. So 40 amps. So number 12 is only good up to 20 amps. Number 14 is only good up to 15 amps. So we're talking about the equipment ground here, okay? Equipment grounding conductor, the green wire in a sense, okay, or bare if we're dealing with residential. But a number 10 would be required for anything up to 60 amps and in that scenario. So that's how we came up with the number 10 on the 40 amp branch circuit that we had going through this conduit, and then the wires coming in after the 125 amp feeder into the panel, feeding the panel, would be a number 6 wire. Number 6, based on, again, the most important one, top 10 code sections, which is 250, 122, and I would hope that, for example, if you ever had a question on this on a state test or anything, you automatically would have that memorized. That 250, 122 always deals with minimum size of equipment grounding conductors, and you would just go straight to that area and figure out the size based on that table. If you did have multiple circuits in the conduit, you're only required to have one ground wire in that conduit, but it has to be based on the largest circuit that's present in that conduit. So here we have a 40 amp, we have a 30 amp, and we have a 20 amp. So we would actually run we would have to base it on the 40 amp, which is the largest circuit going into that conduit. If it was 40 amp, then we know we have to run a number 10, because the number 10, according to the table, number 10 is good up to 60 amps. So that would be the proper sizing in that case. You only have to have one ground wire inside the conduit to cover all the circuits going in there, but it's based on the largest overcurrent protected device that's feeding into that conduit. Article 250.130C kind of talks about sometimes when you have a receptacle that's not grounded and you want to ground it, it's saying a grounding type receptacle on an outlet box or branch circuit extension that doesn't contain an equipment ground is okay if an EGC is run from the receptacle to one of the following. It allows us to run it to the grounding electrode system, the conductor, the panel board, or an EGC of a different circuit if circuits are in the same panel board, or the service at the neutral conductor in the service. So that's not a neutral, it's saying actually a service neutral. So you could actually run it, and a lot of times we will run it. If we did have like a basement, we could actually poke holes through the box into the basement, run it so nobody can see the wires exposed, and then that's a very common way. Or the baseboard, if the lower half of this, for example, I've done this before, is, for example, on the bottom here, if we have a baseboard here, for example, and let's say before you put the baseboard on, you could literally run the wires in the sheet, well, you can open up this little strip here through this bottom piece. You remove the sheetrock and you can run your wire through the bottom of this whole area. You place the sheetrock back on here, but then you put the baseboard on here, and it covers whatever you did down inside of there. It covers it. So what you'll do is you'll run your wire, bring it up through the wall, back down, and you'll go to the next receptacle and then kind of just jumper it back and forth through the wall, in the wall. And that's one way to kind of run it if you didn't have a basement, you're trying to figure out how to run a ground wire in an ungrounded type home. And so there is a way of doing that.